is a convergent solution in birds. It can boost stability without sacrificing even a tiny bit of efficiency. But even when it flew amazingly, that was still just one design, one single shot. So in this video, I'm asking the bigger question: in the huge space of infinite wing shape combinations, what's actually optimal? We'll create a fully adjustable parametric wing, give it real freedom, and let artificial intelligence search through thousands of designs, balancing efficiency, strength, and stability. And of course, once we have a winner, we'll build it for real and flight tested it. So without further ado, let's get started. This is the design I came up with when I tried to mimic bird wing geometry in part 1. It has backward sweep, fundamental for a flying wing, and a dihedral distribution that provides stability without giving up efficiency. But to be honest, when I thought about optimizing this design using AI, I expected the optimizer to land somewhere close to this, maybe a few small changes, a bit more twist here, a little less sweep there, but that's not what happened. This is the wing the AI selected. If you ask me to design this purely by intuition, I don't think I ever would have drawn it. Instead of one simple planform and a straight, consistent sweep, it morphs along the span. The geometry changes gradually, chord, twist, and 3D shaping working together. It's like different sections of the wing are being tuned for different jobs. Why did we end up with such a complex shape? To answer that, we need to rewind and break down how I set everything up. Using AI to optimize and search for the ideal flying wing is not new to the channel. If you haven't seen it already, some months ago I uploaded a video in which I tried to discover the ideal ultimate FPV flying platform. But back then the search was heavily limited. I only allowed a very simple trapezoidal wing platform with just 5 design variables including twist. I ran CFD on about 50 wing shapes, then trained a neural network to predict performance and guide the search using differential evolution. But CFD is expensive. Each design took roughly a full day to simulate. Even with a modest computer, that was only barely manageable, and it still meant months of compute time. So here I wanted to take a different approach, since to give our wing real design freedom I needed way more parameters. Let's use my previous wing as a reference, and I'll show you how I defined the entire 3D shape using 16 design variables. If we start from the top view, the wing platform, the first thing I control is sweep. One parameter sets the leading edge sweep angle, basically defining the wing's main backward arrow. But I didn't want the leading edge to be forced into a perfect straight line, so I added 3 more parameters that nudge the leading edge forward or backward at different points along the span. That's what allows the platform to morph smoothly instead of looking like a simple trapezoid. Then comes the chord distribution. 3 parameters along the span control how much the chord drops towards the tip, so the wing tapers smoothly and stays easy to build. Regarding twist, which is one of the most critical features in a flying wing, I control it with 4 variables, 1 at the root and 3 more along the span. That lets the wing tune stall behavior and longitudinal trim, and it also has a huge impact on the lift distribution. More on that later. And finally, the feature we focused on in the previous video, dihedral or 3D shaping. 5 variables define the wing's vertical curve along the span, so the design can explore the pros and cons compared to a fully straight wing. But before we continue, let's take a quick break because I want to show you something I'm preparing for the next stage of this project. This video is sponsored by GLC CNC Services. I recently ordered a set of custom CNC machine aluminum parts. The process was honestly very straightforward. You upload the 3D model to their website, choose the material, surface finish, tolerances, roughness, and the system instantly gives you a quotation based on those aspects. What surprised me most was how competitive the pricing was, especially considering these aren't off-the-shelf components. Once you place the order, their engineers actually review the design. If something can't be manufactured, they let you know before production starts. In my case, everything checked out, and then a few days after that, they arrived. Honestly, I was impressed. The machining quality is excellent, the tolerances are spot on, and everything fit exactly as designed. So a big thanks to GLC CNC Services for making builds like this possible. And if you can guess what I'm building with these parts, let me know in the comments. Clue, it also uses several load cells like these ones. Alright, now that the geometry is defined, let's talk about how the computer decides what better actually means. In my previous AI video, the goal was mostly aerodynamic efficiency, and that's a great starting point, but it is not the full problem. So this time I'm doing a so-called MDO, or multidisciplinary optimization. If you think about birds, evolution doesn't optimize for efficiency alone. A bird also has to stay stable in messy air, survive real loads on its muscle and bones, and make sense in terms of weight and structure. So how do we turn all of that into something a computer can chase? By using a single objective or scoring function. The idea is simple, every wing design gets graded. The better the wing, the higher the score. This objective function can be simplified as aerodynamic efficiency minus penalties, and it's in those penalty terms where it gets interesting. To include the structural side, we have to remember that a real aircraft wing is a pretty complex structure, usually built from multiple spars running along the span, plus ribs that distribute the loads. But to make the problem solvable, engineers often simplify that complexity into an equivalent model. A common approach is to treat the wing like a single beam that captures the overall stiffness in bending and torsion. And that's exactly what I'm doing here. These structural terms estimate how big is the bending moment at the root and how much the wing will deflect and twist under the lift distribution from the aerodynamics model. And from that, we can also estimate peak stress, which is what matters for failure risk. I also include a term that rewards a smooth, uniform stress distribution. And finally, there is a penalty for extreme 3D shaping, because once you start adding a lot of 3D curvature, the wing generally needs more material, and that usually means more weight. Stability is also included in the score function. First is lateral directional stability, basically how the wing reacts to a gust or a side slip. Good designs naturally create restoring moments and straighten themselves out. Unstable designs get heavily penalized, and they also need to be at least as stable as my reference wing, or they don't survive the surge. Regarding pitch stability, the wing needs a positive static margin, and if a design needs a lot of control deflection to fly level, that adds drag, so trim and stability end up working together in the scoring. And finally, I added a few simple geometry constraints. The biggest one is that the wing area stays fixed at 0.15 meters square. To evaluate the aerodynamics and stability of each candidate wing, I use a Vortex Lattice Method, VLM, through the Python library AeroSandbox. While full CFD can take hours or even days per design, VLM runs in seconds, allowing us to test thousands of wing combinations. And since it is a simplified method, I validated it by comparing VLM results against CFD on the reference wing, making sure the trends match well enough to trust it for the search. So, once every wing can be generated and scored, the next question is, how do we actually search this huge design space? The method I'm using is called Differential Evolution. It starts with a wide variety of random wings. For each generation, the algorithm takes the best performers and creates new candidates by mixing and nudging their parameters, combining them into new designs. If a new child wing scores better than the current one, it survives. If not, it gets replaced. Think about it as thousands of designs competing, and the best ideas are gradually refined into one final winner. So at this point, we had everything in place. Now came the hard part, writing code. The full workflow is far beyond the scope of this video, but anyway, if you're curious, you can find the complete Python implementation on my Patreon. What really matters is that after days of running, testing, mutating, and refining thousands of candidates, the algorithm finally converged. The simulation found a winner, the ultimate flying wing. But a set of optimized parameters isn't an airplane yet. To build it for real, I need a proper, detailed 3D model, so I spent quite some time turning the result into a fully 3D printed modular design. A lot of you have asked what CAD software I normally use, and for complex assemblies like this one, I always trust Onshape as my go-to CAD software, so check the link in the description if you also want to create models like this one. With the geometry locked and the airframe fully defined, it was time to move from simulation to real fabrication. Finally, the fun part, let's build the ultimate flying wing. Maiden flights always make me a bit nervous. After all the optimization, the design work, and the hours of building, there are still so many things that can go wrong. But everything was ready. The weather conditions weren't perfect. It was a fairly gusty day. Still, there was only one way to find out whether the AI-optimized NX2 would truly deliver. Really flew amazingly. This thing is a gliding beast, able to easily maintain altitude with just a small amount of throttle. It feels so stable that I barely need to touch the controls. The wind didn't make it easy for the Maiden, but if anything, it proved a point. Even in gusty conditions, the NX2 stayed composed and predictable. That means we've hit the lateral directional stability targets we were aiming for, and maybe even surpassed them. Okay, I might need to work a bit more on my landings, but the good news is it survived completely intact. On that day, I flew for around 19 minutes, and the 2200 mAh battery was still at roughly a third of its capacity. That means that in calmer conditions, reaching close to 1 hour of flight time is absolutely realistic, which is honestly impressive for a platform like this one. But the real question is, was all the effort actually worth it? Looking at the flight logs and comparing them to the original design, the answer becomes pretty clear. The AI-optimized wing is about 16% more efficient than the previous version. That's not a small tweak, that's a real step forward. Anyway, in the next videos, I wanna dive deep into flight testing, measuring performance and validating the predictions. And I would like to show you why the AI selected this particular geometry, because at the end of the day, this isn't just about one wing, it's a glimpse of what happens when physics, engineering and artificial intelligence work together. And sometimes, the result is a design we might never have imagined on our own. If you want to build your own NX2, you'll find the link to download the files in the description. And as always, stay curious, stay creative, and keep building the future. See you in the next one.